Okay, so today we will learn about linear classifiers. So in the previous lecture, we learned about linear regression and also nonlinear regression, and particularly we looked at the logistic regression function. And what we'll learn about in today's lecture is linear classifiers and the basic model of what we call a perceptron. So the soft and margin perceptrons. So let's just recall what we saw in the previous lecture. So if you guys remember, we looked at the basics of linear regression. And if we have a given data set, let's say a training set that has endpoints, right? So we need to, there are different steps that we need to follow or implement in order to estimate our regression model's parameters, okay? So what is the first step? Anyone remembers? What's the first step? Sorry?
Finding the W star.
Before finding the W star, which is like the optimal parameters of what? Loss function. So the first thing we need to do is define our loss function, okay? So for the linear regression model in this case, but this generalizes to many machine learning problems, especially for building predictive learners, whether classifiers or regressors. So we defined our loss function. So if you guys remember, so it's a least squares loss. So we sum over all our training points. We have the parameters of W and B of our line. So this is what our model predicts minus the ground truth observation and or score, target score, and we square it, okay? Then this is the first step. So after that, what we did, if you guys remember, we defined the compact form, the W tilde vector. So we have the B and the W, and the X tilde. So we have 1 and X. And we defined our new loss function, which is the sum over I, all our data points, training points, xi tilde t, w tilde, minus yi squared. So we got rid of the b scalar value. Now this is the first step. What is the second step, which is important? So now that we have defined, remember guys, our loss function, so maybe we can plot it this way. Okay, so this is our loss function. Let's say maybe it looks like something like that, okay? So we want to find the optimal W tilde star. How do we do that? Gradient descent. So we start off at some initial guess, and then 0, so let's put 0 there, and then we do our, we compute the gradient basically, and the gradient should be equal to what? 0, and then we solve, so there are two ways of doing this, and this is very important. So in this particular case where we looked at linear regression, what did we guys find last time, if you remember? A closed form solution, right? So we were able to automatically derive or write explicitly the mathematical formulation for the W, the optimal W. So we know how to compute it right away. We don't need to perform, updates using gradient descent, starting with an initial guess and, getting the W0, W1 until we get the W star. We got the W star right away. And this is, by solving this equality, and then we got, so here if you guys remember, so we had change of transpose, the inverse of this matrix. So I'll give you more details just to remind you how we build those matrices so you guys can program them if you want to do the exercises in the book. And then what did we have? We have x tilde, and this is the y, this is the vector that has basically all the scores for our training data. Okay? Great, so it has its n-dimensional vector. So here, after computing the W, what is the next step? So that's it, we trained our model. Like basically here we solved our model directly, okay? Imagine if you guys remember when we did logistic regression, we weren't able to explicitly write the W. So what do we need to do in that case? What would be the third step in that case? I'm gonna write it in a different color. So in case we cannot have the explicit closed form, how can we alternatively solve this problem? So we can also, find the optimal parameters for the linear regression using gradient descent. Is it possible? It is possible, right? How is it possible? We just pick, so we perform, we call gradient descent algorithm. So we start with an initial guess, and then we try to minimize our loss. So we start with W0. And then we perform our update. If you guys, what is the update rule? Anyone remembers that? Okay, so I'm going to write it here. So maybe right there. Okay, it's okay. So we have WK equals WK minus 1 minus alpha. So here I'm going to put the tilde. Okay, minus 1. And you will iterate this, you will solve it step by step. So you have several iterations until your gradient is smaller or equal to an epsilon, which is usually a very small number. Okay? What would be very interesting if you want to, check if your optimal solution that you explicitly calculated is correct. You can run gradient descent algorithm. Okay? Find your optimal W tilde through the gradient descent and compare this one with the other one that you calculated. Okay, so that would be a good training for running gradient descent and also comparing the closed form solution to the gradient descent solution. What would this enable you to basically evaluate? It will help us evaluate how good is the gradient descent algorithm at finding the optimum and how fast we can find it, okay? Because you already know your optimum. You have the solution, right? Okay, so this is the training step. So the first thing is defining the loss function, setting the gradient to 0 to find the minimum, and then performing gradient descent if we don't have a closed form. Like in any case, we can perform it, but if we have a closed form, we can directly compute it. But we can solve the same problem by using gradient descent. Now, in the testing step, what do we need to do? So now we have, what do we have? So we have our model. Let me write it down. So we have our linear model. So we had the W star, which has the B star, and so these are the parameters of our hyperplane, okay? So what is the next step to evaluate our model on these unseen samples? So here, what we want to do, we pretend that we don't know the score and we want to predict that, right? And then we want to evaluate the model. So to evaluate the model, we need to compare our prediction on unseen samples with the ground truth that we have, okay? So anyone remembers how we can predict? So for each testing sample, let me write down, for each testing sample xi, I need to predict yi. So the prediction yi will be equal to what? So xi transpose W star plus B star. Okay, so this is our prediction. And after we get our prediction for all testing samples, how many samples we have here? So if you guys know how to count the number of items in a set, so this is the maximum number. This is like min and max. So usually it's max minus min plus 1, right? So m minus n minus 1 plus 1, so m minus n samples. So how many times you will test your model in this case? You run it n minus n times, because you will do m minus n predictions. So after predicting for all our samples, how do we evaluate our model? Using we saw like the mean squared error, MSE. Yes, so accuracy is more like we use it more for classification. So here we will compute the MSE, the mean squared error. And what is the mean squared error, if you guys remember it? So MSE, so it's the sum over our testing sample, so n plus 1 to m. And let me put it this way. So our ground truth, so our prediction plus b star, so this is yi hat minus yi squared. So it's exactly our loss, but we normalize it. So we divide it by the number of testing samples, and in this case it's m minus n. Okay, so this will tell you how good your model is. Great. So right, so here I've summarized this in this table. So step 1, let's look at step 1. So step 1 would be to define the loss function. So this is, you know, the just the least squared loss, and then we define the compact form by introducing these vectors, right? And then we compute the gradient. Remember the gradient, what is the dimension of the gradient vector? It's a vector, right? So here it belongs to d times 1. D is the number of features, how many features you have. So I'll give you more details like in this example. So I'll give you a real example. Now we were able to compute the closed form optimum of the least square regression loss function. And we can also write it in this way if we define x, big X tilde matrix and the y score vector. So this is even a more compact form that is easy to code up. Okay? So, right, so one thing to remember in all machine learning problems is to check the dimensionality of your variable. So this is very important. So in this case, let's look at this formula. So what is the dimensionality of your W tilde star here? Anyone? You guys. So it belongs, wait, to R what? This is the dimensionality, the size, how many elements this vector has. So what is the dimensionality of the W? So your W here, it belongs to RD, okay? And then why it belongs to RD? Because this is a dot product, right? So we're mapping all the features. So all the features in our training sample, if our training sample has D features, we're performing an inner product dot product between our features and the weight vector that we're estimating. So we need to map each feature one, like all of them one by one. So the dimensionality of your W should be exactly the dimensionality of your sample vector, which has D features. So the dot product will give you what? A scalar, right? And then we have a scalar here. So this is why the LWB, it's a loss. It gives you values. So that's just a single value, okay? So, right, so let's look at this. Let's do it step by step. So, for example, let's say we have a training sample. So this is our training sample. It belongs to R2. It has two features. So in this case, it can be, for example, if you remember, it can be the shape of ear, but we want to predict something else, right? It's not classification for dogs and cats. And also the size of nose, for example. And what we want to do, we want to probably look at those and predict something, okay? So I don't know what it is, but we want to predict something. But if you remember, we had those. So these can be any features, like two features. And then what did we define? We defined the X tilde. So the X tilde, we added a 1, okay? So we have 1, X1, X2. So this belongs to R3, right? So what is 3 here? It's D plus 1. And in our case, D is the dimensionality of each sample. It's equals to 2. Now, for the W, what will we have for the W? So the original W is also, it belongs to R2, okay? But for the W tilde, what did we have? We have the B and the W. So here it will be B, W1, W2. So it belongs to what? To R3, because this is a scalar. Now we defined our matrix X tilde. So let's define that. So let's say we have, hypothetically, 4 samples, okay? So each sample, so how do we define the matrix X tilde? We stack vertically all our vectors. So this is for, the feature vector for sample 1, training sample 1, feature vector of training sample 2, 3, and 4. So these are vectors, right? And because they're tilde, so all of those will have an extra element which is equal to 1. So in this case, if we define our X tilde for the first sample, so we will have 1, and I'm going to put some random variables. So let's say the first feature vector has 0, 2, then I'll have a 1 here. This is the second feature vector, so we'll have 3, 4, and a 1, maybe 7, 5, 1, 2, 6. Okay, so this is our matrix. So how many samples I have here? 4, right? And how many, what the dimensionality here, I have 2 features, but I added the extra one. So this is important. Now I'm going to transpose it, because what I will compute here is this exact explicit form. So I will compute this, and I will show you how to do that, okay? So then I need to transpose it. So we need to write it, transpose this matrix. So 1, 1, 1, and then each row becomes a column, right? 7, 2, and 2, 4, 5, 6. So this is exactly X tilde transpose. And then after I compute this, so what do we have? So you guys remember how to do this. So what is the dimensionality of the output matrix? So let me write it down. So here we have D plus 1 times n. So this is the dimensionality of this matrix. This one is n times D plus 1. Okay? So what is the dimensionality of the output matrix? Sorry? N times 1. How did you get n times 1? That's correct. So here, it should be n times n. You said an n, right? So basically, it's an n times n matrix. And here, no, so D plus 1. I got confused. Yeah, it's actually D plus 1. Okay? So, right, and then after that, what should we get? So after that, we need to transpose it. So even if we transpose this one, we'll have also the same dimensionality of the matrix. So it's D plus 1 squared times D plus 1 matrix. Okay? So we compute the inverse of this matrix, and then we need to multiply it by what? By the matrix itself. And the y here. So right here, what is the dimensionality of this one? It's D plus 1, right? So, and we have the W tilde. It should be D plus 1. So what is the dimensionality of the y? Okay, so let me just write it. Okay, so wait, guys. So what do we have here? So this is something important. So look, let me write it down. So here, all of this is the inverse. It's dimensionality. It's d plus 1 times d plus 1. Okay, guys? Get it right? Now, we multiply it. If you look at this formula, we multiply it by x tilde, right? Again. Okay? So what is the dimensionality of your x tilde? It's d plus 1 times what? Times n. Very good. Now, the y, it stores the scores of all your training samples. So what is its dimensionality? It's n times 1. It's a score. It's a vector, right? So this is important if you want to code it up, program it. So n times 1. So if we multiply this, we should get, right, so what should we get here? So at the end, right, guys, I would like you to remember what is the, I'm going to write it down. So just for you to think, I'll give you a minute to think about it. Let me write it down. So W tilde stars is equal to x tilde transpose. Okay, so this is this guy times x tilde times y. So you need to make things consistent because in this one, what is the dimensionality of your output? D plus 1, yes. So we write it this way, or you can put it times 1. It means just one column. But even if you write it D plus 1, so it means like, yeah, so here it's like just a long column vector, okay? So if we multiply those, so the D plus 1, so this will get us like, this should get us the D plus 1. So the n will basically, it should disappear, okay, by doing these multiplications. So at the end, you're going to get your D plus 1 because this, you know, the output here will have a D plus 1, and then a D plus 1 times a matrix D plus, with dimensionality D plus 1 by D plus 1. It will give you just a matrix. You're you know, multiplying a matrix by a vector. So you're going to get the same dimensionality, okay? So it's just this guy's dimensionality is like D plus 1 vector. Because here, what are we multiplying? We're multiplying a matrix by a vector. So we're going to get a vector that has D plus 1 elements. So the n will disappear, okay? So, and you can do that. This is just simple linear algebra. So do you guys understand how to do this? So you can see, this is important. And, you know, like, I know that I'm writing all those equations, but, you know, if you run it on a simple example, and you check all the dimensionalities, it's very important, right, for you to check those because then you will be able to implement them, like to code them, okay?